Okay, welcome back. In the previous few lectures, we have covered the derivative and its applications. In this lecture, we're going to take a step away from the derivative for a moment and consider the limiting process again. Just now, we're going to look at limits of where the x variable is tending towards infinity or negative infinity. And how does the function behave when x does that? So maybe I'll just write that. So we will be concerned with the end behavior of a function on an infinite interval. Okay. So what do I mean by this? I think the best way to illustrate it is with maybe an example function. Let's consider f of x equals to 3x squared all over x squared plus 1. And this function more or less looks like this. We'll wait to draw the picture of this, the graph of this function. And I just want to pose a question to you. And so a lot of times when you're dealing with mathematical problems, it helps to get an estimate first before you try to actually work out anything. And what do I mean by that? I mean, well, let me pose the problem first, I suppose. So problem or the question to answer. So how does f of x behave as x goes to infinity, or as x goes to negative infinity? So that's the problem at hand for today's lecture. Okay. Now, back to what I was saying earlier. So before we start really manipulating this algebraically and applying limiting concepts, it helps sometimes to look at the function and kind of estimate what you think it should behave like. In this case, as x is really big or really negative, right? What do you think it should behave like, right? So just looking at that function. So this is our function f. This is 3x squared over x squared plus 1, right? Now, let's ask ourselves. Let's focus on x going to positive infinity, x getting arbitrarily large, right? So let's just look at it and say, okay, when x is really big, like if x is 1 billion, right? And we look at this, right? This division here, right? That's 1 billion squared, right? Plus 1. Does that 1 really matter at all? No, right? 1 billion squared plus 1 is basically 1 billion squared, right? So in my mind, when I look at that function, like, okay, this function is approximately the same as 3x squared over x squared, right? Basically, it's basically the same thing. But this right here, x squared divided by x squared, is just 1, right? So what are we left with? We're left with just 3, right? So already I have an idea about the behavior of this function as x gets really, really large, right? And since these x is like the variables are being squared, right? The same thing will hold if x is really, really negative, right? If x is negative a billion, negative a billion squared is positive a billion squared, right? So in both cases, like this function, I think, is going to behave like this function, 3, right? And if I draw the graph of the thing, it looks like this. It's like 1, 2, and 3. And the function looks like this. That's the graph of that function. So now this would make sense, right? Like just if we're looking at this picture, like if we take x going this way, the function's graph is like hovering underneath this line 3. Now it might not reach it, right? It might not ever be actually equal to 3. Again, we're getting an approximate to what the original function was, but it more or less behaves like 3. And to me, and actually in a lot of instances, knowing more or less the behavior is good enough to understand whatever application that you're looking at, right? And this notion needs to be formalized now. This is like me getting an approximate idea of what this behaves like. Now we're going to formalize it with the definition. So definition. There's 2 parts to this. So we say that the limit as x approaches infinity of f of x equals L whenever for every epsilon greater than 0. So recall, typically when you see an epsilon in mathematics, it's some small positive number. So for every epsilon greater than 0, there exists some m greater than 0 such that the distance from f of x to L is no more than epsilon whenever x is greater than M. So this is the formal definition of an infinite limit existing and being some number L. Okay, so it's wordy, there's Greek symbols, and it can be confusing. But the idea is simple. I don't know if you remember that when I first talked about like the limiting process, I never really said absolute value. I said the distance, right? Because the absolute value between like the difference is the distance between those 2 numbers. So what this is saying is no matter how small of a positive number we pick, if this is true, then the distance in the function to that limit is small, is as small as we like. Whenever x is greater than this m, and this m is dependent on that epsilon. So for example, like whatever distance it is, like here, like whatever that distance is right there, right? Then m would be right here. And then any x you pick over here, it's going to be smaller than that distance. Okay? And you can pick any epsilon positive. So you can, like somewhere down the line here, it's basically going to be on it. It might not equal it, but the distance between the graph with the output of the function and the number 3 is going to be tiny. Okay. In a similar fashion, we can say that we can define the limit as x goes to negative infinity. Okay, so limit as x tends towards negative infinity of f of x equals L whenever for every positive number epsilon there is some, I don't know, I'll call it n this time, n less than 0 this time, such that the distance from the function's output at x to the limit is less than epsilon whenever x is now less than n. Okay, so x is greater than m up here, but now down here it's less than n. That's because we're looking at x going this way, right? So like, if we pick some distance epsilon, like it's like this, right? Whatever that distance is, then maybe n would be right there. And we pick anything more negative than n, the function's output is always going to be like within that distance to the number 3. Okay, so these are the first definitions that we're going to work with in this this lecture. Okay, so all right, what can we do here? I need to erase this, right, because I have another definition that I need to introduce. Okay, and that is the definition of a horizontal asymptote. In fact, that graph that I just erased, right, there was a line that the function wasn't ever going to pass above, and it was getting arbitrarily close to. That was a horizontal asymptote. So the formal definition is that the line y equals to L. So this is a horizontal asymptote. Of the graph of f when the limit as x approaches to infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. Okay. That's how we define these things. That cutoff line, basically. The cutoff line that the graph of the output of the function gets arbitrarily close to. That's important. Okay. So now I'm going to state a theorem. And this theorem is it's very natural to think about, actually. So a very obvious theorem. So if R is a positive rational number, so a rational number is a ratio, a fraction. Or it doesn't have to be a fraction, it's like a ratio. Like 2/1 is a rational number, it's equal to 2, or 1/2 is a rational number. So R is just some rational number. And C is any real number then we have this equation. So the limit as x approaches infinity of c over x to the power r, that's equal to 0. Okay. Now, in addition, we'll say if x of r is defined for x less than 0, which might not be the case. Like if r was 1/2, it's like the square root, right? And we can't take like square roots of negative numbers without invoking imaginary numbers. So we're just dealing with reals right now. So if that is defined for negative x, I mean, so like maybe r is like some like odd power, and then there's no worry about like square roots of negatives, right? So that is defined for x less than 0, then the same equation holds as x tends towards negative infinity. Okay. Now, why would this make sense, right? So what is going on here? Now, this one is when x is tending toward positive infinity, that's the easiest one to think about, and that's the one we'll discuss for a moment. So c is just some number, right? C is just some fixed number, it's fixed. Okay. So that thing is fixed, right? But x, no matter what r is, r could be like taking like a really big like root of the thing and making it small. But no matter how, like as long as r is a positive rational number, at some point, x is going to be, x to the power r is going to be larger than c at some point, right? At some point, because x gets to grow forever and c is fixed. So at some point, the denominator is going to be larger than the numerator, right? Which means that this value becomes less than 1, right? As soon as that happens. And then the next x we pick, larger, next x we pick, larger, next x we pick, larger. This is starting to grow way bigger than that fixed c, right? And any, like, it's like a number divided by an arbitrarily large number, which makes this thing as close to 0 as we want, which is, that's the definition of the limit. Does that make sense? Right, like imagine like if it was a 1, right? Like 1/2, 1/3, 1/4, 1/5, where are we going, right? Where's the function going? It's going to 0, right? Like, so like, I'll do it like here. So f of x, maybe it's equal to like 1 over x, right? So then we can make like a table of the values, like x, or that's going to be a terrible table. I'll do it here. Like this function here, let's make a table. So x is here, f of x is here. So when x is 1, it's 1, right? Let's put in a 1 right there. When x is 2, it's a half. When x is 3, the function evaluates to a third. Dot, dot, dot. This goes on forever. When x is like 1,000, the function's value is 1 over 1,000. Smaller, right? 1 over a billion would not be that far away. 1 over a billion squared. Like this thing is heading towards 0. It's never actually going to equal it, but it's going to get arbitrarily close to 0 as x gets larger and larger and larger and larger and larger, close to infinity. The same thing holds for a c. And at some point, this thing in the bottom is going to be larger than that c. Okay. C, so like r in this case, by the way, if you didn't notice, r is 1. 1 is a rational number, so the power of x here is 1. But it could be like a half, it wouldn't matter. Eventually, this thing is getting arbitrarily close to 0. Okay. And the same thing will happen here if x of r is defined on negative numbers. X to the power r, right? And r that wouldn't work, it'd be like a half in that case, because then we can't take square roots of negative numbers. Okay. So let's look at an example. Let's look at the limit as x approaches infinity of 5 minus 2 over x squared. And I didn't mention it, but we did discuss this when doing limits last time, like earlier in the semester. Limits are additive, right? The limit of the sum is the sum of the limits, okay? But before even breaking that up into two limits or even anything like that, or applying this theorem, whatever, let's just look at it and think for a second, right? What does this function behave like when x is really large, right? What is it behaving like? So so 2 over x squared. So when x is equal to square root of 2, this is like a 1. It's like 5 minus 1, it's a 4. Okay. And then when x is 3, it's like 2 over 9. Right? So it's like 5 minus a smaller number, right? So when x is a billion, it's like 5 minus 2 over billion squared. Like 2 over billion squared is a really small number, right? So what do you think that this is behaving like? Yes, it's getting closer and closer to 5. And without applying that theorem, without doing any algebra, we can get a sense of where it's going. Okay, we're estimating it. But if we wanted to write out like a solution to check our guess, our estimation, we would say, okay, limit as x goes to infinity of this thing here, 5 minus 2 over x squared. The limit of the sum is the sum of the limits. I think of different, subtraction is like a sum as well. It's just adding the negative of the thing, right? So the limit as x goes to infinity of 5 minus the limit as x goes to infinity of 2 over x squared, like that. The limit of a constant is just the constant, right? So this will be equal to 5 minus, and then we can apply that theorem. C is 2, right? And R is also 2. So this holds, which means that this is going to be 0 by that theorem. Which is equal to 5. So applying that theorem, we verified our intuition, right? We verified our estimate. But this is good, especially for those of you that struggle with the operations and getting lost in the actual putting your pen on the paper. It helps to have an estimate before, to have an idea of whether or not your answer is in the right realm, right? If your estimate, even if your estimate is wrong, right? If your estimate is small, right? And your solution is large, you better double check things, right? If your estimate is the same as your solution, then you could be confident, right? Okay. I need to take a picture of the board for my notes, because I didn't write out good notes today. Any questions about that? Simple enough? Okay. So, all right, this is the easiest example. Now we're going to run into ratios where there are several tricks, not tricks, there are several techniques. I hate saying tricks. There are several techniques that you'll need to have in your bag of like techniques to solve, right? And luckily, they all kind of are basically the same. The techniques are fancy versions of multiplying the function by 1. Let's look at another example. Find the limit as x goes to infinity of the ratio 2x minus 1 all over x plus 1. Okay. Now, there's no like, there's x's on top, there's x's on bottom, right? So if you immediately look at this, you don't see a constant in the numerator. And you shouldn't be thinking about this yet. What should you be doing? You should be trying to get an estimate of what that thing looks like when x is really big. So our estimate, well, when x is really, really large, I'll use a blue marker for the estimates because this isn't the solution. This is just me trying to get intuition about what's going on. So all right, so 2x minus 1 over x plus 1. So ask yourself the question, when x is a billion, right? And we're dividing by x plus 1, right? They're like, division syncs these things together, right? So when x is a billion plus 1 is basically a billion, right? So this is basically for large x, right? But then the same thing applies for the numerator, right? Like these are tied together because they're being divided by this, right? So we can look at these two together right there and say, okay, when x is a billion again, does that minus 1 really matter? No. But what's that? This is just 2. So to me, now that I've done this little bit of estimation, I'm like, oh, this thing surely should be around 2 when x is really big, right? So I have an idea ahead of time. Okay, so what does the solution look like? I'm not going to have enough room here because I have to introduce a new technique. So if we just go ahead and try to like plug, like not plug in, but just like look at where the numerator and denominator go together, or go individually as x goes to infinity, we'll get something like this. So like, we'll get that, right? Infinity over infinity. This has a special name, which I always misspell. I don't want to misspell it. This is called the indeterminate form. infinity over infinity, or 0 over 0, or something like that. Something that doesn't make any sense. Right? However, we know ahead of time that this thing should go like be behaving like something, right? So whenever you encounter the indeterminate form, you can typically, if you know it should go somewhere ahead of time, and it looks like that, there's a technique or several techniques that you can apply. Here, it will help us if we have something like this, right? It's going to help us if we have a constant divided by the variable x. And the way that we can invoke that is by multiplying this expression by 1. What do I mean by that? There's like the original expression, right? What happens if I multiply this by 1 over x divided by 1 over x? And we can write 1 over x because x is getting arbitrarily large. It's not going to ever be 0. It's past 0. It's way big, right? Isn't this a 1? Something divided by itself, it's a 1. It doesn't change anything. So what happens when we distribute that in there? So we still have our limit here. But now we're going to have, looks like, so 1 over x times 2x minus 1 over x times 1, right? Just distribute it in. So 2x times 1 over x is just what? 2, right? In fact, I'll write it out just so you see it. Right? I just distributed in. Now 2x times 1 over x is just 2, right? The x's divide out. And then minus 1 over x. X times 1 over x is just a 1. And plus 1 over x. Okay? Yeah. Well, they're divided out, right? X divided by x is just 1. Well, the negative and positive, like, what do you mean? Oh, no, no. So there's no, this numerator is not the same as the denominator. You can't divide out there, right? Even if you factor out a -1, sometimes you can do that kind of stuff, but in that case here, you couldn't. But we're done. Because we have a constant divided by x, a constant divided by x. As x gets arbitrarily large, what is that equal to? 0, right there. That's a 0. What are we left with? 2 over 1. Exactly.
So we just assume that 1 over x will equal to 0?
It does by that theorem. Because the limit says, it says the limit as x goes to infinity of any constant over x to a rational power is going to be 0. So that goes to 0 as x goes to infinity, and so does that. And we're left with the 2 and the 1, which just leaves us with 2. But again, notice that these are matching up. So it's almost like we verified our estimate. And this, so I should probably mention this, that if there was an additional question, like So like maybe, so y equals to 2 is a horizontal asymptote of the graph of f of x equals 2x minus 1 over x plus 1. So like whenever we find these limits as x tends towards infinity, we're finding horizontal asymptotes, because that's how they're defined. Okay. Now, this like technique here is, it's going to pop up in a bunch of these rational type, like that's a rational expression right there, right? And you're just trying to enforce through some clever multiplication of 1, you're trying to get a constant over x, because you know that that type of structure, that type of expression goes to 0 as x gets arbitrarily large. Okay. So let's look at another example. I guess this is another good one. So find the limit as x tends towards infinity of, say, 2x plus 5 all over 3x squared plus 1. Okay, so you don't have to do the estimates. I'm just highly suggesting that you do them, right? For your own sanity when going through the problems. So let's do it. 2x plus 5 over 3x squared plus 1. Okay. You have to be careful about when you do the estimates in that this, like if there was like a number over here, right? And you're subtracting, you have to be very careful about the things by themselves, right? Like these are bound together because together this is dividing this thing. These are bound together because they're being divided by that thing, right? So we can ask questions about the numerator and denominator here respectively and kind of see where we're going. So I seem to keep on saying a billion, so let's just imagine x is a billion. Does that 5 matter? Like 2 times a billion plus 5 is basically 2 times a billion, right? So, and again, it's approximate, right? I'm just getting close to it. And 3 times a billion squared plus that 1 means nothing, right? So it's basically that.
So every single time we have a plus something, it's okay if we remove it to do the estimate? Like it won't really.
I'm not going to say that that's a rule of thumb, right? I'm just saying to think about it. Because like, what if it was like an X or something, right?
I'm gonna ask you,
Yeah.
what's the biggest constant?
I'll use any arbitrarily big one. I'm just saying a billion because like we're getting big.
I mean, we say 2x.
Well, like it just depends. Like if that 1 was like a billion, right?
Then that won't make a difference.
That would make a difference. But then we would just say maybe like 2 to the power of a billion, which then that a billion means nothing. Right? It's all relative to what you're adding, because really like these like constants here, like x grows forever, right? And that's just, you have to remind yourself when doing this. So I'm very cautious, and I don't want to say that you can always like just get rid of the additions or subtractions. I'm just think about it, right? And kind of like maybe trust yourself on that a little bit. And I'm going to do a bunch of examples so that you'll see like how I did it, right?
Are we gonna be able to do one also where like x is not infinity?
What do you mean?
Like, is there ever gonna be like a problem of these, but where x, let's say, approaches like 30?
We did those at the beginning of the semester,
Oh, okay.
right? That is the limit as x tends towards A or C or whatever, right? And in that case, like in that case, you wouldn't do the estimates
Mhm.
because x is going towards a fixed number.
Mhm.
Here we're using estimates because x is getting arbitrarily large. It actually makes it like easier to me.
Mhm.
Okay. So here, this expression is basically that expression when x is large enough. This reduces to what? 2 over,
Great.
right? Now, when x is really big, again, like 2 to the power of billion, right? This is gonna, like, this denominator is going to be arbitrarily large, and that numerator is fixed. Right? So imagine, what's 2 divided by 3 times a billion? It's basically nothing, right? It's basically 0, right? So when x is large enough, this is basically 0. And we trace ourselves back, and I'm confident in saying that this thing more or less behaves like the constant function 0 when x is really, really large. Okay? So, but how would you verify this estimate, right? Like your solution needs to be verifying it, but at least you know that ahead of time. So my guess, that limit's 0. And even like with like, this is one way of estimating it. Just looking at it again, I had a thought like, okay, like if x is like 2 to the power of billion, right? Which is like way more atoms than there are in the entire universe. Like 2 to the power of billion is like, we can't even like imagine how big that would be, right? So then it's like 2 to the power of billion squared, right? This is huge, right? In the denominator. In the numerator is 2 to the power of billion basically, right? So the square of it is underneath it. So this is going to be larger than that. And as x gets bigger and bigger, this denominator is growing a lot faster than this, right? In fact, this leads me to an interesting thought. It's not in the textbook and it's not a technique that I don't know that it's taught, but like, think about it like this, like, is that the rate of change for the numerator, I mean, the denominator, is the rate of change faster than the rate of change for the numerator? If this is growing much faster, if this is growing faster than that, then at some point it's going to start looking like it's going to 0, right? So like, I don't know. This is like me going on a tangent. So if f of x is equal to 2x plus 5, and g of x is equal to 3x squared plus 1, right? So I'm like focusing in on the numerator and denominator. Now, what's another way of measuring instantaneous rate of change? Like rate of growth is measured by the steepness of the tangent line at that point, right? So the derivative tells us the rate of growth, right? The paradoxical statement, instantaneous rate of change. So how do we do that? Well, we look at the derivatives. F prime of x is equal to 2, right? And g prime of x is equal to 6x. You see that? So what's happening here? This is measuring the rate of change for each one of these things, right? Rate of change of that and that. This piece here, which is the numerator, is changing at a rate of 2, right? However, the denominator is changing at a rate of 6 times whatever x is, right? Which means that this is growing and growing and growing, that's staying the same. This is speeding up as x gets larger. This is always growing at the same rate. So at some point, this is going to overtake that. Okay, so that was just another way of looking at like why I have more evidence to believe that that thing actually is 0. Yeah.
Which one would you accept as an answer? Estimated?
Neither. The actual solution is what I'm about to write. These are just ways to like make sure that your solution is in the right ballpark. So again, if we tried to like evaluate the limits as x goes to infinity for there and there, it'd be infinity over infinity is that indeterminate form. So we would see that infinity divided by infinity, but we have evidence that it does go somewhere. So then we'd say, okay, let's try to apply some trick, not trick, technique. So let's look at the limit as x goes to infinity, 2x plus 5 over 3x squared plus 1. Now, again, the goal algebraically is to get something that looks like a constant over some x variable, right? And here I see that the highest power for any x is a 2. So what that indicates to me is that if I want to eliminate x squared right there, I'm going to have to divide everything by x squared so that that x squared goes away, which would also take care of that one. And you'll see what I mean in a moment. So we're going to multiply by 1 over x squared divided by 1 over x squared. Oh, I need to close off my parentheses. Okay, so then what does this equal? So let's see, limit as x goes to infinity of 2x times 1 over x squared plus 5 times 1 over x squared divided by 3x squared times 1 over x squared plus 1 over x squared. Just distribute in, right? And then we see 2x over x squared is 2 over x. So we'll have 2 over x plus 5 over x squared all over, so 3x squared over x squared is just 3. Plus 1 over x squared. And then that theorem that I wrote on the board earlier tells us what? It tells us that this goes to 0 as x gets really large. So does that, right? So does that. So what are we left with? We're left with 0 plus 0 over 3 plus 0. 0 divided by anything is 0. And we verified that our estimate worked. Okay. Or no, we didn't verify, but we're more confident that the answer is correct. Okay. All right. So more examples. All right, so let's look at this one. So 3x minus 2 over the square root of, what is that? 2x squared plus 1. Now, we should probably start with an estimate, right? And I would be lying to you if I didn't mention that doing these estimates, if you're careful about them, you'll get the correct answer right away. But you have to be very careful. That's why I'm not saying that you should use that. In fact, you have to write this out typically. But again, mathematics is not, to me, as a mathematician, this is a part of it, but to me, the estimate and the thinking and like the wondering about what's happening, that to me is more about what mathematics is than this. Okay. So let's think. Let's say 3x minus 2 all over root 2x squared plus 1. All right, x is a billion, right? So like, and x is a billion, 3 times a billion minus 2 is basically 3 times a billion, right? And 2 times a billion squared plus 1 is basically 2 times a billion squared, right? Squared.
Can we move it up?
Well, what I was going to say next is the square root of x squared is just x. Well, the 2 we can ignore that 2. That 2 stays in the square root
Because it's multiplying.
because it's multiplying, we can take the square root of x squared, and that's just x. And then x divided by x is just 1. And we're left with 3 divided by root 2. I think that's the limit. Again, I have to be very careful, right? Like you have to know your like rules for radicals and exponents, which that there. Are we okay with that? Okay. Okay, so let's look at the actual solution. This one's going to be rough. What do I want to do? The reason why it's not rough, just the reason why it's annoying to do the same technique we were doing is because there's a square root right here. So we have to multiply by something. Like we got to get rid of that x squared, right? We need to make that a constant divided by something. So we have to choose something to multiply that will go into that square root. Like we can't just multiply by a number. We have to by like 1 over x or something. We have to multiply by possibly 1 over square root of x. And you'll see what I mean in a moment. So the limits as x goes to infinity of this expression, so 3x minus 2 all over root 2x squared plus 1. So I'm going to multiply by this. What do I want to multiply by? I also want to get rid of that x in the top. Right? Like I need to divide by x up here, and at the same time divide. Well, let's just do this real fast. We'll do it one piece at a time. So I'm going to multiply 1 over root x. Oh, this is going to work out nice. That I got this problem from the textbook, and I think I just now figured out why they chose it. That's what I'm multiplying by. Isn't that just 1 over x? Right? 1 over the square root of x squared. So look what happens in the numerator. 1 over x times 3x, that'd be just a 3 minus 2 over x. So the numerator is going to be taken care of. We'll have like constants divided by x. And here in the bottom, we'll see this. I'll just write it out. Limit as x goes to infinity of 3x minus 1 all over root x squared, like that, all over root 2x squared plus 1 divided by root x squared. And that's what happened. And like, again, this is a 1, something divided by itself. We didn't change the expression, right? So hopefully all of you see the square root of x squared is just x, right? So this is going to be the limit as x goes to infinity of, so 3x, so this is dividing that piece and that piece, right? It's dividing the 3x and the 1, right? So what will that be? That'll be 3 minus 1 over x in the numerator. What 2?
The -2.
Oh, that should be a 2. Yeah, the original problem was 3x minus 2. So then this will be a 2 right here. Okay, thank you, by the way. And then here we have radicals, like the square root divided by the square root of something else is the same thing as the square root of that divided by that term. Like that. So what that means now is that that x squared is dividing that piece, and that x squared is dividing that piece now. So what are we left with? We'll have our limit here. So in the numerator, it's still 3 minus 2 over x. And then in the denominator, we have square root of 2 plus 1 over x squared. Okay, now we're good. Constant divided by x, constant divided by x squared. Those pieces there go to 0, right? As x gets arbitrarily large. So that means that this is going to be equal to 3 minus 0 over the square root of 2 minus 0, which is just equal to 3 over root 2. It matches up with what we thought it should be. We can be moderately like, okay, like this is correct. Now, your dumb textbook might ask you to rationalize this, which means that you would take your answer and then you don't want any radicals in the denominator. So you multiply it by another fancy form of 1 to get rid of those. So square root 2 times root 2 is just 2. So then we'll have 3 root 2 over 2. So your solution that like you'd most likely have to give is like to click on would be that. To me, I don't care. 3 over root 2, but just a heads up to rationalize your expressions before you make a choice of an answer in the homework, in the textbook. Okay. So, by the way, I should mention that, can we like, what about this? Like, are we allowed to look at this limit? So as x goes to negative infinity of 3x minus 2 over root 2x squared plus 1. Like what is that going to be? Can we just like think about it for a second? I don't want to work it all out, but can we think about it? It is defined because as x gets negative and negative and negative, it doesn't matter inside of here because x squared, it'll turn positive, right? So that's fine. But now up here, it's like negative, right? So it's negative up there, but in here it's the same as it was before. So I'm assuming, and you could work it out in the exact same way, that this will be negative 3 over root 2. Right?
Mhm.
And if you did the estimate, you would agree with that, right? Like this basically behaves when x is really negative, like negative a billion. Like that plus 1 doesn't matter, and negative 2 doesn't matter. You'd work it out, and that's what you would come up with. Okay. So let's look at another one. Find the limit as x goes to infinity of sine of x over x. Now here, estimates, it might be difficult for you to estimate it, right? Because the sine function, right, is going to oscillate between -1 and 1 forever. Like as x gets larger and larger, it's never going to be fixed, right? So this is not a constant, right? But we do know something, and I just said it. The numerator is oscillating between -1 and 1, right? And the denominator is getting arbitrarily large. So what's our guess as to what that should be?
0.
Right. Like, in fact, we can kind of, the solution is somewhat easy. So we can say, maybe like since -1 is less than or equal to sine x, which is less than or equal to 1, right? We have that -1 over x is at most sine x over x, which is at most +1 over x. Right? And just divide everything by x. And we're considering x positive, like x is getting arbitrarily big, we can see that, right? So then, what happens if we take the limit on all sides of that thing? Let's see. Take the limit as x goes to infinity of 1 over x, which is less than or equal to, so negative of that, that's less than or equal to the limit as x goes to infinity of sine x over x, which is less than or equal to the limit as x goes to infinity of 1 over x. I just take the limit on all sides of the inequality, and I observe that that thing on the left-hand side, that goes to 0, right? And that thing goes to 0 as well. How can a number be greater than or equal to 0 and also less than or equal to 0? What does that imply? It means that it has to be equal to 0, right? Like if it's greater than or equal, and then also less than or equal, it has to be equal, right? That actually has a name, by the way, the technique that we just applied. It's called the Squeeze Theorem. But why remember that when we just look at this thing and say, oh, it's bigger than 0 and less than 0, and it has the opportunity to equal, it has to equal. Like really, it might surprise you, like how little I actually remember about like these statements of the theorems and stuff in calculus. I found it easier and better for me when learning math, like because I used to be terrible at it, but like it became easier once I just stopped trying to like fill my head with all that stuff and just thought about the ideas and like kind of remembered some techniques. But a lot of this stuff is unnecessary if you just kind of slowly break it down into pieces. Okay. Now, there are cases where the limit is what's called unbounded. Like for example, like if we look at the limit as x goes to infinity of x cubed, that's unbounded. There's nothing stopping this thing. There's no horizontal asymptote. It just goes, right? So basically what this is saying is that, and I don't know, for the sake of not standing anymore, because my ankle hurts, I'm not going to write down the definition. I'm just going to tell you it. What does this mean? It means that for any positive number you pick, for all x, there exists like a cutoff where every time you put in a bigger x, it'll be bigger than that positive number, right? It's just like at some point, like we know what this graph looks like, right? It looks like this, right? You pick a number, any positive number you want, like, I don't know, k, any positive number, right? Then somewhere on here, there's an m, where every single x you pick, oh, that's not going to work right there. Maybe here. There's an m, so that any x you pick, the output's going to be above k. And always getting, so, and that was for that k. If you pick any k you want to pick, there's going to be one of these such that it goes bigger than it. That's what this definition means. And then the term that I use is called unbounded. Right? There's no upper bound to that function. Whereas what all these other things, like, they're bounded in the extreme case, like when x is arbitrarily large, they're basically stuck next to something. Okay. Okay, so that will be the end of this recording. So I'm going to go ahead and stop the recording